Hello everyone. Thank you very much for your joining. My name is Jakub Hudec, and together with my colleagues, we organize this event focused on drive and fly-by-wire. I'm happy that I can stay here and I can invite our great speakers, Tomáš Haniš, Tomáš Nouza, and Ondřej Karas. And we have three great presentations, three great speakers. And I would like to tell you about format, about presentation. After presentation, you will have a few minutes for some 1 to 3 questions, and finally, I hope we will have much more space on the end of this event. So, thank you very much. Take a seat and enjoy. Tomáš, could you go?
Thank you very much. Thank you very much for the invitation, and it's nice to be here. My name is Tomáš Haniš. I'm from Valeo Technical University in Prague, Faculty of Electrical Engineering, Department of Control Engineering. Don't worry, you are here correct. I just changed the name from drive-by-wire because quite often the drive-by-wire is related to, in automotive definitely, how the intake valve is controlled. There is no longer a physical connection. There is a mechatronic connection or system, and that's basically the picture we will follow us through the course of this presentation. But I really like I was playing with the words a bit. I changed the drive-by-wire to the full-time for authority control systems. It is also inspired from the aerospace, from engine control system, where you have a FADEC. So what does it mean drive-by-wire then? What is the difference between conventional? Actually, this is really funny. In Czech, it is really ambiguous. In Czech, we have really nice phrase for conventional setup, drive-by táhlo, by puller, or physical connection. That's the one in red on the left side. And drive-by-wire, by the way, we don't have a really nice word or name for the drive-by-wire in Czech, other than the direct translation, that's strange. So what's the difference between drive-by-wire and conventional setup? Yeah, I'm from the university. I'm used to communicate with my students, so I need some response from you. So any suggestions? Is there any difference? Or at the moment, if you go to any car on the parking lot, is it one on the right, one on the left, or one on the right? And what is the fundamental difference between the by táhlo or by puller or by wire? Okay, so not you. So the main difference, or the key differentiator, is that the conventional setup, some form of the mechanical energy is transmitted. It can be a directly mechanical energy. If you have steering wheel, you have a torque which is directly transmitted to the torque on the pivot point of the wheel. If it is a brake, it is either the hydromechanical or air suspension, air brake system. But some form of the mechanical energy is directly transmitted. And I said that this is a fundamental difference. So what is transmitted in case of the by-wire? Yeah, worse than my students at the university, I have to say. Okay, so in case of the by-wire setup, the information or the data is transmitted from a driver and to the whatever system it is at the end. And of course, that brings us the fundamental disadvantage and advantages of the conventional versus drive-by-wire system. So I try to, it's not all of them, it's just something from the top of my head. But I believe that's really important to focus on this aspect, which is it's directly derived from the either mechanical system or mechanical energy transmitted by the mechanical system or the information. So first of all, if I start on the conventional setup, the simple requirements that basically were the conventional setup really shy. If you say that there is a steering wheel, if I turn it by whatever factor or whatever value, I want my steered wheel to be turned by the same amount. That's as simple as that. Of course, today's system, the electronic power steering, it's more complicated. Don't get me wrong, but at the end, it is basically the transmission of the information from the driver to the system or to the chassis system. Of course, connected to that, you have really big chance or big advantage of the reliability because you have really simple and really robust system. That's of course it's play in favor of the certification, because if you have a steel bar, it's as long as you don't mess it up and use really chunk steel bar, then you should be fine. Feedback, definitely you have direct feedback up and down. That's basically it. If you start to basically work through the process of the, I would say, really ingenious mechanical system, mechanical design. Don't get me wrong, I really adore those systems. I believe they are really nice piece of machinery. But basically, this is the limitation of the conventional system. If you want to change anything, it's really hard, and it doesn't matter if it is. If you want to change anything on the level of the drive-by-wire system or steering system, brake-by-wire and drive-by-wire, meaning the proportional, you have to change the mechanical parts. You need to have a steering column coming from the driver to the front wheels. If you want to have a rear wheels driven, then again there needs to be some mechanical pass from the steering wheel to the axle, which is quite challenging. First of all, we have quite a lot of requirements for safety. There is a direct bar pointing towards you. Not the best idea in the crash situation. For the space in the car is definitely challenging, because you build a car and then somehow you squeeze a driver there. Because first you have to make sure that you can drive the car and you can operate the car. So this is the disadvantage of that. Fixed architecture and the no modularity. What I mean by that is that basically you design the car from the basically for the mechanical path through the car. You have to place your system, like the engine, transmission, then all that in the car. Make sure that everything is well placed, well balanced, if you want to have a nice vehicle dynamics of the response of the car. And then you have passengers. If you want to go from one car to another, you are starting all over. There is basically very limited, even though in Volkswagen they managed to do it quite nice, but you have very limited modularity in this sense. One other thing is that the setup of the system is really hard to change. I have some driving habits. My wife, she might have a completely different one, and there are quite a lot of compromises, quite a lot of optimization upon which you build a system, and then this is once built, then it is fixed. In order to do that, you have to come up with, as I said, with the optimization, or at least good feeling of the designer who is really skilled, and I really respect those guys. I believe, again, this is don't get me wrong. I'm not saying this is wrong setup, but in order to accomplish this, you have quite a lot of simplification and the assumptions which are constraining the performance, the ability of your system, in order to manage human. In order to provide a functionality for a human, I mean, is that the human can manage the system, because at the end, the ultimate functionality, or let's say higher level functionality, is pushed to the driver. As I said, you are transmitting the mechanical energy. This is one of the critical part, difficult manipulation of that. There are plenty of the systems where if you want to change the mechanical energy, I mean the command which is sent or provided by the driver, it's quite hard to come up with some system. Usually it is again really nice, but some mechanical clockworks you can introduce them. You can do that somehow, but it's again once designed, then it's fixed and that's done. The even bigger challenge is if you want to have some manipulation without a feedback to a driver. Sometimes it's really critical for a driver to have a feedback coming from the car. No doubt about that. Really nice example is parking assistant. You know, we are sitting in the car and there is a crazy spinning on the steering wheel, and you know sometimes it would be better, or in some situations it would be better if you don't have that, or if you don't feel lane keep assistance, stuff like that. If you don't feel the feedback in the system, and that's particularly really tricky to introduce in the conventional setup. There are plenty other examples, both for the cons, advantages and the disadvantages. So this is just some coming from top of my mind, as I said. If you go to the right side, it's basically the inverse, or fairly the inverse, because what you have, if you have a mechatronical system, you have a sensor, there is some ECU or some computer which will digest the information, the command coming from the driver, and then spit on the other side the command to some servos or some mechanism which will eventually act on the car. This is fairly flexible system, fairly modular, because you can have the same setup basically as long as the actuator is strong enough. In worst case, you change the actuator. And you can use this setup for quite a variety of the vehicles in size, in the use of the car. Either that being the high performance cars, 911, Porsche 911, that's a really nice car, all the way to the everyday commuter car where you want to have completely different output or feeling of the car. So this kind of the flexibility, modular design, you can have the similar setup where basically you have front wheel steering. You can have the same system in the rear axle. Yeah, just plug it in, and then it is just a software to code or to provide. The biggest advantage of the drive-by-wire system is that you can completely relax the constraints on the vehicle, which is good and bad. Don't get me wrong. Definitely, it gives you the possibility to play or fiddle with the vehicle. And the question is, if it is, from my point of view, it's no longer a car, let's say vehicle, where either all those designers with really fancy interiors and stuff in the vehicle. Also, how many wheels you have, where you place the wheels, where you place the electric engine or whatever type of the mechanical power for the proportion you are using. So this really ease up your process. The biggest advantage of the drive-by-wire system is that you have really easy manipulation of the information, because it is just some data or really information which is provided by CAN bus or whatever. Then you do the math and you speed up the output to the actuator. And of course, first of all, if you want to add something to that, you just write the line of the code and that's it. Of course, don't get me wrong, there's a functional safety and stuff like that. It's not that easy, but it is just a system. You don't have to. You have to develop new mechanical system. And I believe this is a really important part, as I said, just a software, because the software will eventually implement the functionality or any functionality you want to have. And as long as you don't need any functionality, basically you don't need a drive-by-wire. If you want to have as simple a system as steel bar, that's it. That you can't get better than steel bar. But if you start to pile up the functionality you want to have, it can be other system, active safety, whatever you name it. You need, or you are basically approaching the drive-by-wire realm because of the ease of the implementation, because of the flexibility you have, and because of the architectural relaxation of the vehicle. One other key aspect is the system level optimization, and this is really important. We had really nice discussion with Tomáš, the next speaker, about this topic, because at the moment most of the systems in the automotive are done on the component level. Again, don't get me wrong, that approach is of course it was needed, because you have fairly complex system. You have to chunk it to small boxes in order to develop them. But right now it's 2023. The amount of the functions and the components piled up so high that we start to be drowned in the software design for the automotive, and that's because we are on the mainly on the component level. And of course, if you're on the component level, as I said, it's really fairly easy to organize the work, and then you need to have the integration phase, of course. But as I said, there are really good reasons for that. If you're on the system level, you can unlock quite a potential coming from all the systems in the car. Active safety, energy optimization, that's basically the outcome of the system level optimization as an outcome of the drive-by-wire architecture and the drive-by-wire system. Definitely there is no free lunch or free meal, free cake, so you have to pay the price for that. The price is quite hefty because the complexity of the system grows quite a lot. The reliability and the robustness and the safety, eventually the safety of the system is the key issue, and it has to be addressed. And connected to that is definitely the cost, because at the end it is just the money. You have to pay. All that comes to the certification, because that's the ultimate goal, or not goal, the test the software development needs to pass in order to fly, or not fly, to drive, to be in car. And one of them is also the feedback, because by cutting the steel bar, you are sacrificing the feedback, and you have to repay, or how to say, you have to offer something else in order to basically pay for those shortcomings. So what I mean by the drive-by-wire, is this drive-by-wire? So who think it is a drive-by-wire? Just so 2 out of, it's not many, 3. Yeah, we discussed that. Frankly speaking, I don't think it is a drive-by-wire. It's the first step towards a drive-by-wire. I don't believe this is a drive-by-wire. It's just the beginning of the journey, really long journey. The key point here is that the ultimate functionality is pushed to the driver. So even though basically you have some instrumentation which can be understood as a by-wire, you don't really use the benefit, or you don't really unlock the benefits coming from the system. So from my point of view, I'm really sorry, this is the first worst thing you can do, because you pay the price for the instrumentation, you pay all the actuators, you pay the extra certification for the software, but you don't really use the benefits of the drive-by-wire. But as I said, this is the first step. We will get there. So what I really think drive-by-wire is something like that, where you can have crazy designs of the car, and I'm not here to discuss the design of the car. Yes, it is in wheel hub motors or whatever, but you can have let's say really tricky instrumentation of the car, where each wheel is independently steered. The brake system for the independent wheel, that's here for ages. And that's basically it. That's the drive-by-wire we need in the car. Yeah, the last thing is 4 engines in one power wheel. So that's the same. There's the same configuration. The key part here is to have a chauffeur, to have some functionality which will provide you, which will augment the capability of the everyday commuter, and it will provide you with some benefit you can have from the drive-by-wire system. One of that might be the active safety. There is a really nice example. If you are driving a horse, whoever rode the horse? Nobody. Okay. So if you are riding a horse, you are giving him basically which direction you want to go. You are not telling him where to put his hooves or his legs, and that's the difference between this one and that one. Because here we are still in charge of directly controlling the wheels. Here there is some some functionality which will provide you, and that's the key part, which provides you the functionality you can use and you can benefit from, and that functionality is going to pay for the extra cost, extra complexity of the system. The other example is the aerospace or aero. But that's topic for the other speaker. So okay, so is drive-by-wire system good, or is it better, or is it any good? It's really hard to say. There is plenty of aspects, plenty of sub-criteria to take into account. Again, I try to pick few of them. Definitely not all of them. If you just go through that, it's hopefully it is reasonable assumption. Usually the worst part is the cost. Every manager, if we start to speak about drive-by-wire, they are really worried. And then when we come to the cost questions, they are really exhausted. If you are talking just about the cost, drive-by-wire system will be always inferior to the conventional system, because you just pay extra, and if you don't have an extra functionality, it doesn't make sense to do that. So I think it's really important to understand the cost per functionality or per function. That's the other thing. One other part is the safety, because nobody wants to read articles about the accidents of the car crashes, and how many injured or dead people. Again, if it is just the safety itself, the drive-by-wire system, I mean safety meaning the reliability of the system, the drive-by-wire system will be inferior to the conventional car fairly easily, because you can always blame the driver. In this case, the drive-by-wire system is responsible for the safety, and in that case, it is the active safety. That's the first part of the story. The second part is the redundancy. I didn't stress this out, but I hope it starts to be clear that if you don't have the redundancy in the system, the drive-by-wire is again questionable. If you really need the drive-by-wire system or not. What I mean by the redundancy is exactly as we discussed before. Each wheel independently steer, each wheel driven, each wheel braking system for the individual wheel. And then you can have redundancy. If you can't steer with your front wheel, you still have the steering capability of the rear wheel, and so on. So based on this redundancy, you can really increase the safety or active safety of the system, and you can have fairly reliable and trustworthy system to use. So what about the other parts, the hardware implementation? That's something we will go through the presentation each time, because as I said, all managers, they are always really worried about this part, that you need to have an extra sensor, you need to have an extra actuator there. Yeah, that's the price we have to pay if you want to increase the functionality, if you want to increase, let's say, the ease of the implementation of the new functions. But frankly speaking, the hardware instrumentation, it's how different it is, the drive-by-wire car from the conventional car today. I mean, we have steer-by-wire. All luxury car, they have rear axle steering. So that's steer-by-wire. That's nothing else. From the hardware point of view, don't get me wrong. Now we are talking just about the instrumentation and about the hardware. So if I have a rear axle steering, that's steer-by-wire, and it doesn't matter if it is rear or front. Frankly speaking, if we have electronic power steering system, it is again by wire. We are just too worried to cut the steel, but at the end, if the software would be implemented wrong, you can't really compete with the electronic power steering system. So at the end, it's really important that that sensor register the wish or command coming from the driver. Regarding the brakes, I mean, for ages we have ABS, we have ESP, so we can individually actuate the wheel. Regarding the engine, I mean, if you have internal combustion engine, usually we have just one. But if you really want to take the advantage of the active or regenerative braking, you need to have more. There was a really nice article coming from the Formula One driver. I'm really sorry, I'm terrible with names, and this was one of his biggest argumentation towards drive-by-wire, because if you have 4 engines, you can have much higher efficiency of the regenerative power. Everybody wants to have 4x4, at least that's my child dream or boy dream. But everybody knows that Subaru Impreza, it's drive-by-wire, it's 4x4, it's awesome car to drive, Audi Quattro, and so on. So regarding that, that's basically covered. So what else we have there? The functionality, we touched that a bit, but the functionality basically translates to the software design and system level design. As I said, the potential there is that you can go from the component level to the system level. And there is a huge potential basically everywhere. If you wouldn't design the power electronics, inverter or control, electric machine controller, you can't really increase the efficiency on the component level. Right now we are at, I don't know, 90, 95, something like that. For every percent or fraction of the percent, you pay a lot. If you go to the system level, it's completely different story. That's what we will talking about later on. About the software, as I said, at the moment the automotive has a bit crisis regarding the software. There is a really nice example, Tesla. Even though I don't really like to use this underbelt argument, but basically the Tesla, there was a few or many software developers who just came and say, yeah, I don't care about the conventional stuff. We will code that everything from the clean sheet, and they manage in 10 years to be 10 years in front of the conventional OEMs. So maybe there is something about that. Colleague of mine, or my PhD students, they were at the conference IEEE Intelligent Vehicles. It was in Aachen, and there were several speakers discussing this issue. And I'm not talking about the infotainment. I'm talking about the software of the vehicles. That at the moment, the integration of all the components, verification phase, it starts to be really expensive, and it starts to be almost unbearable to go. Again, the advantage here is that if you go to the system level, from the component level to the system level, the integration is there because you are on the system level. You don't need to do the integration step from the component level to the system level. So you can have, let's say, more efficient cheaper software development and the application phase of the software. What are the potentials of the drive-by-wire? As I said, we pay a big price by all those assumptions for the conventional setup. What we did here, we just say, okay, we don't care about the assumptions that the car is driven by steering front wheel or front axle or rear axle. Just relax everything. Just let the car freely move. And this experiment was that there was a car placed on the basically roundabout on the circle, and what we measure is basically three indicators: the power you need to stay on the circle, what is the maximum lateral force or acceleration you can generate or produce, and basically the minimal turning radius of the vehicle. Let's see the maneuverability of the car. This was just a steady state experiment. There was no control, no system like that. It was just to trim the car to be circling around, and then we compare the fixed rear axle, the conventional car, with the fully relaxed system. And then we received I would say peculiar results. First of all, we thought that there is a mistake somewhere in the methodology, but looks like there is not. We found that we can reduce the power consumption in this scenario by 20%, meaning that there is up to 80% of the power basically wasted in the lateral, or say the rolling resistance induced by the lateral dynamics. Regarding the active safety, in this case it depends on the configuration, but there is a basically 30% increase of the maximum value of the lateral force compared to the conventional setup. And definitely the maneuverability, it depends on the maximum steering angle. In this case, it was 30 degrees. And we receive up to 40% improvement in the maneuverability. So we took those results and we say, okay, but we need a system to provide us with the functionality. Again, we are coming to the functionality. Provide us the functionality which would confirm those results. But this is, as I said, this is just a steady state maneuver. But basically, there are more what you can do. If you have the redundancy, you can have a zero emission transportation. The biggest issue of the zero emission, basically the Euro 7, even though now it was revised, but it doesn't matter. The zero emission at the moment, the critical point is the tires, the brakes, friction brakes. You can't get rid of the friction brakes, or can you? If you are in the emergency, what does it mean emergency? Your battery can't accept more power from the regenerative braking. If your battery is half filled or CO 50%, you can fully brake with your electric machine or electric engine, and you don't use the friction brakes. Then the issue is the low speed, and the issue is if there is something wrong with the battery, or if the battery can't accept more energy. What are you going to do without the friction brakes? If you have redundancy, this is the emergency case. By the way, this is the bachelor thesis of Tomáš. He's over there. He's a really shy guy, and he asked me not to mention him. And he proved that basically with this system, first of all, you will just tear your tires apart, but eventually you would stop the car. This is the emergency maneuver. If you are going downhill and you want to stop by any means necessary, you can do something like that if you have redundancy. And basically the system I will be talking about later on provide this functionality, I would say right away, because it's the way how it is constructed. Okay, then transportation of vehicles. If you want to transport or move your your house. I mean, we are in Czech Republic. We are moving churches, right? So this is nothing. So what you are going to do? You have to develop a new vehicle. You have to develop some chassis, something which will hold the car. What you can put the church, or in this case, just a house, on, and then you can drive. So basically, you are building a vehicle which is suitable for the job. This is the other example. It's, just some chassis. What's really interesting here is that in both cases, it was also the case for the church, even though it's speed up eventually. All those vehicles are driving really slow. And the reason is that they are using the kinematic model. We will discuss that later on. Again, our approach is that if you have drive-by-wire, it doesn't matter where you put your wheel or wheels. It's referred to as a corner module. This is the example of the corner module coming from the Hyundai, but there are plenty others. I believe the first patent came from Siemens, but I may be wrong. About 15 or 20 years ago. So the corner module is well known. So again, you can fit those modules around the house or whatever, and then you can just let the house drive on its own. And the question is how to control the wheels, the functionality. We can have the transportation for everybody. This is the conventional car, and as okay. I'm really terrible this time. I'm really sorry. This is the conventional car it is a Tesla, okay. But as I said, there's a steering wheel, there's engine wheels. How do you want to fit a poor guy with the wheelchair in such a configuration? As I said, it was built for the car. I'm sorry. It was built for the car, and then the human is somehow fit inside. So we can have a completely new possibilities with the drive-by-wire system for the HMI. By the way, this is your system. This is coming from the Valeo. Where basically the military application is that it can track the movement of the head of the pilot. In that case, it's used for the aiming. But if it's working for the aiming, it can be used to aim for the aiming of the car. And in that case, you don't need your feet, possibly your hands, and it also relaxes the constraints for the construction of the vehicle. Yeah, let me go really swiftly through that. It's a bit of physics. As I said, we are dealing quite a lot with the over-actuated, that's the keyword, meaning that we have more degree of freedom per motion of the car. I can use the steering wheel steering of the front axle, rear axle. I can have the differential braking or actuation of the car. But eventually, the ultimate parameterization of the vehicle or anybody in the plane is it's in this case speeds, and that's unique. So here we have the longitudinal, the lateral speed, and the cornering speed, the yaw rate. And this is something we want to have. It means that we want to accelerate straight, as simple as that. How to do that? We need to produce a force in the CG. So all that is generated at the CG. And as I said, we want to go straight. So there need to be just one force in the CG straight ahead. How to produce any forces on the vehicle? We need to use our tires. So we place the brakes. If you want to slow down, we place the electric engine there. But you have, even now, you can see that you have infinite number of the possibility how to distribute the force on the traction force on the wheels in order to receive this one. The transformation from wheels to there is unique. That's fine. That's physics. Physics takes the hard part for us. It's solving all the differential equations there. By the way, this is it's a rather silly example, but you can see that this force is same, even though I did some really strange configuration, and the resulting force is still same. So the question is how to go from this force, basically how to go from the CG to the wheels, and that's really hard to do. Usually it is done the dynamical inversion, which is, I would say, quite unrobust because it relies on the model of the vehicle. We did that in different approach. Yeah, from now on, basically you can skip that because this will be just me talking about our stuff. So what we did is again, just forget about any constraints coming for the architecture of the vehicle, and what is the best coming from the component level, of the architecture of the vehicle. What is the best way to parameterize the motion of the vehicle? We already discussed that. That would be those three velocities. So I call it the vehicle velocity vector. This generalized. There is the doesn't matter. And then we want to go from here to there in the way that it would respect the inversion problem of the car. Let me just go really quickly through that, because this is basically some technical stuff, how it's done, and thanks to that we call that the feedback control allocation problem. The control allocation problem is the fancy word how to allocate the traction forces, for example, and we can do that via the feedback. In that case, the system is fairly robust, fairly simple. We have the complexity of bit more than ESP system, and it provides all of that because it provides the vehicle motion control. So you prescribe the motion of the vehicle, and the system, the feedback allocation control system, will provide you with this functionality. Again, functionality is really important stuff. What you pay for that, you need to have over-actuated system. You need to have relaxed system. Otherwise, you reduce the possible performance of the system. Other benefit is that it's fairly modular. It doesn't matter how many wheels you have, as long as you know where they are. So you need a position vector to each wheel. And that's it. You don't need anything else. So this is really suited for the corny modules of the car. But not only, it can be also applied to I mean, you need a certain degree of freedom. So Škoda Fabia, I'm sorry, there is no extra degree of freedom we can benefit. So yeah, we can't use that. This is basically that you can use the same stuff in connected vehicle, either virtual or physical. But I wanted to show you the last part is we were doing one project with Volvo trucks, where this is the conventional setup of the Volvo at the moment, and this is our crazy stuff where you can see that everything is steered, everything is braked, everything is driven. By the way, Tomáš was also involved in this project. And if I go to this slide, we received quite interesting results. Again, we thought that we are wrong. But as I said, there is plenty, and this is the fully dynamical system in place. This is not a steady state. This is really tracking of such a track. And as I said, there is plenty of reserve or energy or power to be saved in the lateral direction. Somebody told me, okay, if you're on the highway, you don't care. You can see that it is fairly flat. You have several turns. Okay, still we managed to have about 10% reduction or increase of the efficiency of the vehicle. There is one other benefit, because you have trajectory tracking inherently built in. Because this is the drive-by-wire system, and you can see that we have much better tracking of the reference system compared to the conventional one. Again, the speed, you can see that we have quite a lot of speed loss for the conventional car to the drive-by-wire car. I mean, there are plenty benefits and drawbacks. Don't get me wrong. It's always up to you to say what I need, what are my requirements. If the requirement is driver steer or turn the wheel, turn the steering wheel, turn the wheel on the tarmac, that's it. You don't need a drive-by-wire for that. I think that's it from my side. If you have any questions.
Thank you very much for your presentation. We do not have a lot of time, so there's time for one question, and who is online can send a question to the chat. So excuse me, but we have time only for one question now.
I have a question. Is that a real time, or you know the trajectory or not?
That's a really good question. Yes. In this case, yeah, because if you have trajectory tracking, the biggest issue is that if you have the feedback system, just the feedback system, it will basically, let's say this is the reference trajectory. If you have just the feedback system, you will pass this point, and then you know that there is something wrong, and then you start to steer the car. So you need to have, it's called look ahead information. Otherwise you can't have that that functionality. So we have look ahead information. Yes.
From the praxis point of view, it means we are like 20 years ahead, yeah? or behind. Yeah? So what in Valeo we mean by drive-by-wire? It's some system that I can over some, not wire, but over some bus. In most cases, it's CAN bus. We can control the movement of the car. So we would like to control the braking of the car, the acceleration, the steering. But not only that, we would like to also maybe change the gears, like let's say to change to reverse. We may want to turn on the lights on the car, maybe to horn somebody, or to control the wipers to, for example, clean the vision of the camera that is behind the windshield. So all these things we would like to control from the computer or from some embedded ECU. And that's what we understood by drive-by-wire in normal combustion cars, the cars that you can buy on the market. Why we need it? Because it's something like must-have for the ADAS development, for the driver assistance systems. We as the Valeo are producing the sensors, the cameras, radars, lidars, whatsoever, but we need to join these sensors with some functions, because that's the motivation when somebody would like to have it in the car. They would like to have emergency braking system or adaptive cruise control system. They don't care which vision the vehicle uses, if it's based on the radar or camera. They would like to have the function. On one place we can use some simulator to develop the functions in computers and hope that it will work in real conditions. Or we have to test in reality, and it's always better to test in the reality, because then you will find the cases that you cannot even imagine behind the keyboard. So all the functions needs to be proven on the test tracks and in open road traffic conditions from the real world, because our cars are driving in the real world. And therefore we need something that we tell to car, now it's time to braking, and the car will really brake. So for us, we abstract it under the term drive-by-wire, where I will try if this is working. Maybe not. I don't care. But the gray box in the behind is our computer that is hosting the drive-by-wire system that is capable to control the engine to accelerate, or to control the brakes to brake, or to control the steering wheel based on our commands. So this is motivation why we need it. And how to get the car. It's quite tricky. There are several options. You can buy the steering robot. It's done mostly on every NCAP testing. If you have the star rating for the vehicles, how safe they are, you need to repeat some test cases every time, like the same way. So this is something that human driver cannot do efficiently. So you need that the vehicle is controlled over some trajectory that you define, and therefore there is some actuator that you put on the steering wheel, it turns for you. There are actuators that are touching the accelerator pedal and brake pedal, and you are verifying what the car will do in these conditions. But it's quite unhandy to sit in the car when there is this steering robot. So there is another option. You can buy some solution from the companies that are producing the cars for disabled road users. You can buy the system that is certified, everything is triple redundancy, and ASIL D system that you can control car by just joystick. You will replace even the steering rod with some engine. You will have again the actuators that are touching the brake and accelerator pedal. There is one issue. The system was designed to control the vehicle fully. And in case you will ask the car to kill you, it will just kill you. I mean in the way that you are driving on the highway 130 kph and you will ask the system, okay, now it's time to fully steer to the right. It will steer and you are rolling over. And there is no way how to prevent it because it's triple redundant system. So once you send the command to kill me, it will kill you. You don't want to kill yourself in the car, but you are creating software that is full of bugs, and the bugs will kill you. So this is something we would like to prevent. And if we bought the solution for one of our car, but there was the issue that really with the steering. It was very hard for the human driver to overpower the steering of the system. So we considered this car as unsafe for public usage. So we are using it only on test track. Next option you have is to ask some engineering company or university to create such a car for you. There are engineering companies that are capable of doing it, but it may end up in the situation that they will fill the trunk of the car with this technology, and there is no place left for your systems. We use this way as this was the only suitable option on the market, that you are using the existing vehicle actuators. The throttle in the car is controlled electronically. There is no more mechanical friction. Yeah? So you can use this electronic actuator. You can use the braking system to just send the brake command over the CAN bus if you know how. And the same is with the electronic power steering. If you know how, if you understand the logic inside of the steering ECU, you can turn it into the mode that it works for you. So if you have some deep knowledge, you are able to adapt the car to your needs. And as I said, there are a few companies that are able to provide you with such a car. But it's expensive, it's expensive. The reason is there is quite a lot of engineering, and there is not that much companies that are buying these cars. So we initiated a joint project with University of Ostrava to create such a system for our needs. We came for a much better price, and as we had the opportunity to directly influence the development, in the end the system was like this size. It's just the flat space in the trunk on the side. This is normally not used. So this was a very successful project, but it's not the thing how we do it always. Usually the best thing is just to do it yourself. And this you can do only if you have some expertise in the vehicles. That, for example, with this OEM car producer, you were working on some project with some ADAS system, so you already know how this ADAS works. So we are able to use the, let's say, correct way how to treat the control units in the car. So there is some L2 system. L2 means there are 5 levels of autonomy of cars. So most of the cars has level 2. It means it can like keep you in the line for line keep assist, and it can do the adaptive cruise control for you to actively keep the constant distance from the vehicle that is in front of you. So these cars are called level 2 systems, and usually they are working based on some camera combination with radars. And in one of these ECU, the function is hosted and is controlling the vehicle gateway that is then controlling the rest. And they also interchange some signals between themselves. And what you do is that you cut the communication between this system and the vehicle, and you modify the content of the messages. So you can then ignore the input for the camera and input for the radar, because you don't care what they see. You just keep them in some happy state, that they are some idle, that they are not casting the errors to the vehicle information cluster. And whatever they are normally transferring to the car, like accelerate, you will replace with your commands. And this is what we call drive-by-wire in Valeo. I know it's completely different word. And that's it. Yeah? And then the next step is how to get such a vehicles on the roads. Because if you are doing such modifications, you are completely breaking all the homologations. So you cannot drive on your license plate. So then there is proceeds how firstly you have to ensure the safety for yourself. This is how we are doing it in Valeo. So firstly, vehicle is providing you some signals about its speed, steering wheel angle, wheel ticks, how the wheels are rotating. So all these signals we are reading, and we are ensuring in some device we call one-way gateway that we will not modify these signals like in reverse order, or if we will generate something behind, that it's not propagated back to the car, that we will not get the car into some error state, or that we will not disrupt the communication between existing ECUs. So this is like one way, just only reading access for the signals. Then we have in the blue box some Valeo ADAS system that's most probably full of bugs, because it's in the development phase where the system is not fully tested. It's some very rare prototype. And if I will be in extreme case, you can put there just random signal generator that will be driving the car. And it will be still considered safe, because you will put there safety gateway that will filter all the control commands that your blue device is providing. You will verify if the control signals make sense, if they are in safe range. And only if you pass through the safety gateway, this is accepted as control signal to the drive-by-wire system. And the main benefit is that you verify this system just once. Because if you do the solid verification of it, you can replace the blue part multiple times, next software version, next software version, next software version. But as long as the green part is safe, your vehicle is still ready to go. So what this safety gateway is doing, it's doing several checks. Firstly, we would like to verify whether the signals are there, whether they are updated. So all the signals needs to have some CRC, some checksum, and some message counter. And if you are not receiving the signal longer than 100 milliseconds, you are forcing the vehicle into the safe state that it's no longer accepting the signals. It may happen that the ECU from the control system just crashed and it stuck. And you don't want that the vehicle will continue with the constant acceleration. In that case, the vehicle will just stop accelerating and report to the driver that the control system is out of order, and the human driver that is sitting in the car takes over the driving. Then the next step is the maximum speed check. Because we are in the Czech Republic, we would like to comply with the common regulations on the road. So there shall be no meaning from the control system to violate the speed limits. Of course, German colleagues are asking us why we have these conditions. We cannot fully test it on our highways. But let's say we are working for Czech testing. So as long as we are testing in Czech countries, we have some Czech procedure. And if you go to Germany, then do your German procedure, and you can validate this condition. And then the tricks, how to ensure the safety, are these two graphs that are speed dependent. So firstly, we would like to verify that as your speed is rising, you are limiting the maximum steering wheel angle available on the steering. The faster you go, the smaller corrections you shall do, because otherwise you will roll over like from Cobra 11. So this is one approach, and second approach, you are limiting the maximum acceleration and deceleration. You don't want to feel the autonomous emergency braking on the highway in heavy traffic, because otherwise the people from behind will kill you or will crash you in better case. So again, based on the speed, you are limiting the maximum deceleration and acceleration that is allowed. The maximum acceleration, this is not that critical because vehicle cannot accelerate that much unless you have some sport car. But we are limiting to 4 meters per second square, and this is something that usually you can do with speed less than 30, and then it's limited for normal cars. Next step is to test it. Yeah? Therefore, we have our polygon in Milovice, where we have like 2.5 kilometers straight runway, where we can do whatever we want. And these are some pictures how it looks like there. So we really spent there whole day, sometimes multiple days, by testing whatever scenario we can ask for the drive-by-wire interface through the safety gateway, if it's really safe. And only if we will pass all these tests, we can consider, okay, this car is safe for public usage. And then then goes the legislation. So in Czech law, we have the F plates. It looks like this. It's green. And if your car has these plates, you don't need to have homologation. You don't need to have, I'm not sure what is English term of technický průkaz, but you don't need this paper. You just need to fulfill these 3 requirements. So you shall comply with electromagnetic compatibility, that you are not producing noise that strong that you will cancel all the policemen's radio stations. they will really stop you. Also, you shall not have any sharp edges on the car. It's for pedestrian safety. And third thing, that you shall have your lights that are according to Czech law. And once you fulfill these 3, you can do whatever you want with the car, and you are okay for road usage. You can, for example, replace your windshield with this wooden desk, and you don't care that you don't see outside. But everything you do wrong with the car goes to your company, and if the Minister of Transportation evaluates that you did something wrong, they will just take the F plates from you and no more testing for your company. They will remove all the plates, not just from the one car, but from all your car fleet, and you can close the business. Yeah? So you must be very diligent what you are doing with the cars with the F plates. But for all in the audience, if you will spot the car with these plates on the road, take attention. It's prototype car. The things that the guys are doing inside can look crazy, but they are just testing our functions. Or maybe these are Škoda guys that are testing something else. There are several more companies that are privileged to have these plates. But our process is that once we have the plates on the cars, we really knew what we are doing, and safety is our highest priority. I have some more bonus videos for you. The first one is how we controlled our car over the tablet. Once you have the drive-by-wire system there, you can do whatever you want. So, for example, write a simple Android application that is translating the tablet movement to the acceleration, braking, and left-right you can steer. Okay, there is no other use case than just to amaze the public that we are capable of this. Yeah? We will never sell it. Second video I will comment afterwards, because there is a lot of text and you will be reading the text and not listening me. It's Tatra, and we have the privilege to have this vehicle in our next to our buildings, and we are using it. So it was created in cooperation again with the University of Ostrava, that created the interface there. And basically they created it according to our requirements. Therefore I am highlighting it there. But the main thing is that we are not speaking only about passenger cars. We are speaking also about the heavy machinery. Okay, so this is last slide from my presentation, and now is place for your questions. I told you I will be quicker.
Okay, thank you very much, Tomáši. And do we have any questions, Tomáš? I know about one question.
Já se omlouvám, já tolik anglicky neumím, to položím česky.
Určitě.
Ale nemluvím to. Pokud jsem dobře poslouchal kolegu, pro aktivaci vozidla je potřeba bezpečnostní smyčka. Ta bezpečnostní smyčka je zastřešená safety gateway a jede to ve dvojkové soustavě aktivačních vstupů. Jaká je časová prodleva autodetekce při státě signálu na těch aktivačních vstupech? To znamená, než ta bezpečnostní brána vydá povel tomu vozidlu k nouzovému zastavení. Protože ztratí nějakou aktivaci na důležitém vstupu v té bezpečnostní smyčce.
Okay, I will translate to English. I hope I have catch the question. If not, then please correct me. So there were two questions, and I'm not sure if it was to our system or to the serial system, but the question was how big is the delay till the control system reacts, whether it lost the control. Am I right? So in our case, it's in about 100 or 200 milliseconds. And but if you are like in the commercial sphere for emergency braking, because you were asking for emergency braking, it shall be something similar, like that you lose one or two messages in the sequence. The messages are usually going every 20 milliseconds or every 40 milliseconds, and if you lose 2 or 3 consequent messages, you consider it like false. So with this, we are compliant with this.
Oh, we are in milliseconds, yes?
Milliseconds, yeah.
Okay, thank you very much.
And in our system is also the recovery state, because it may happen that the system is recovered, and in this case we are waiting following 10 seconds till we will allow the control to the system again. We have more conditions. For example, if the driver presses brake pedal, whenever during the testing, it's always disabled for 10 seconds at least. Yeah. If you press the throttle pedal for more than 95%, it means like kick down. It means also we would like that the car do something else. We are switching off the system for 10 seconds. Yeah.
Okay.
Maybe I have a question.
Mm-hmm.
What could be the real life use case for like remotely controlling such a huge vehicle like that?
Okay, the real use case for remote controlling Tatra vehicles, I would say it's from defense industry, where you can use it for autonomous convoys. But the second use case is for mining, for example, that you can have the automated fleet of the vehicles inside of the mine, where you have some supervisor system that is controlling which vehicle goes where, to automatic loading of the soil, and to move it to other place where the cars will automatically unload. Yeah. So this is one real use case. Both of these use cases are really used more than 10 years already.
Okay, Tomáši, thank you very much for your presentation. I would like to invite our last speaker, and it's great that we can.
Right, thank you for the invitation. I really appreciate it. So I'll talk about multivariable aircraft control using dynamic inversion. Basically, I've been working for Honeywell for about 5 years now, out of which 4 years were on what we call the compact fly-by-wire project, which is basically a little box that you can fit into light aircraft, like let's say 2-seater aircraft or 4-seater aircraft, which normally didn't have fly-by-wire before. And well, we're now basically designing this to be, let's say, universal and adaptable to different kinds of aircraft. And similarly, as with the drive-by-wire, there is no advantage of putting such a expensive system, let's say in a Cessna or an aircraft that can fly without it. So our use cases are now mostly electric vertical takeoff and landing aircraft. And I'm unfortunately not allowed to talk about the current project, so I'm gonna mostly give you like some general background, how this works in general, just some math, and talk a little bit about some past examples where this has been used. So first of all, let me, I guess, introduce Honeywell in Czech Republic. We have this three main sites. The main site actually is in Brno. I've been based there most of the time, but recently moved to Prague, and we now have also a small engineering team in Prague. And basically, this is the history since 1993, basically. So now, in aerospace, we basically do mostly autopilots for business jets, general aviation, helicopters, and now also for these what we call urban air mobility, which are basically these future, air taxis, what they call them also. And we also do some space development. It's a different team, not a team that I work in, but basically we do a lot of like data link and internet through satellites and things like that for aviation. All right, so now starting with the main topic. Basically we're using feedback control, so we're reading something from a sensor or sensors, acting upon it, and then commanding what we call effectors, which I'm going to talk about shortly what those are. But basically, those are different devices that can somehow change the trajectory of the aircraft, so they can basically produce forces or moments acting on the aircraft. So we can represent this aircraft as a over here. Then we have basically the response of the aircraft that's measured by some sensors. We have this feedback loop, and then we have some commands from the pilot. The pilot usually only has two hands, so the pilot can command at most, 4, let's say, engineering variables, if you will. So, like for example, they can command, velocity forward, lateral, up, and then maybe one angle, or they can command, acceleration forward, change in, flight path angle, or change in track, etc. So they only can do a limited amount of commands. And on the other hand, the aircraft has a lot of effectors, sometimes 20 or more for these electric vertical takeoff and landing aircraft. They have a lot of rotors that are spinning independently, and they can sometimes tilt. They can, sometimes change their angle of their rotor blades, etc. So all that has to somehow be controlled automatically, because the pilot wouldn't have the capacity to do it manually. So for our applications, basically the fly-by-wire is essential. There is no way to do it without fly-by-wire. And then, well, over here comes our control law, where we basically produce those commands. So first, some basic definitions. So we have these what we call body axes. They are basically aligned with the aircraft. The x-axis is forward. The lateral one is y-axis, and the vertical one is the z-axis. And then we define these rotations. Roll, which is basically like a roll like this. Pitch, where you pitch the nose up or down, and then yaw is like a heading change. So you basically rotate about the vertical axis. I'm showing the image of the F-35 on purpose here, because actually the control law that we're working on has been in development since the 90s, and one of the applications that it has been used for was the X-35, which was basically the prototype for the F-35. And that was the exact same control law that we're now reusing for other applications, except that obviously then it diverged once Lockheed started the formal development for the F-35. They took whatever they needed and started their own process. So I'm not sure how much of the original control law is still there, basically. But it's a good example because the F-35 has a lot of effectors. So to define like what effectors are, they can be control surfaces. Like you can have these flaperons, for example, that can move up and down, and so they can create basically a vertical force, which will then induce a rolling moment on the aircraft, mostly rolling moment, but basically in all three axes. And you can also have the engine. The engine can increase or decrease the thrust. It can also be vectored, by swiveling the nozzle in different directions. You have this lift fan in the front, which is connected to the engine, but it's also controlled independently, so you can basically generate different amount of force in the front. This is the F-35B, which is basically the vertical takeoff and landing version. Then you have further control surfaces, and then you have these roll posts, which basically blow air, and so they can create rolling moments. So basically, you can with this you can control the aircraft also when it's hovering, stationary. So then your control surfaces, which are basically the aerodynamic effectors, let's say, don't have any effect at low speeds because they need air blowing over them. So this is an example where I don't remember how many, if you sum up all these degrees of freedom, but it's a lot. Basically, the pilot will not be able to control all of them. So we need some system that's going to basically do this control location, where it's going to distribute basically the pilot commands into the different effectors so that the aircraft will respond the way that the pilot is asking to respond, and so that the pilot can also control it more intuitively, because they can control something that's directly related with where the aircraft is going to move, instead of controlling different RPMs or different degrees of deflection of different surfaces. Okay, now let's add a little bit more to our feedback response. So unfortunately, the world is not perfect. So basically, we have these different disturbances that act on the aircraft response. An example disturbance could be turbulence, or just change in the wind, which basically happens all the time. We call it wind shear. It could be also any kind of imperfections in the let's say, response of the effectors, so they don't necessarily always respond exactly the way that we ask them to respond, etc. Then once the aircraft somehow reacts, we measure the reaction, but the sensors are not perfect. They have some noise in them. They can also be subject to other different kinds of errors that can be, oscillatory, or they can be like a steady bias, or all sorts of different errors. So unfortunately, then what the controller has to work with is not perfect, basically, and we need to be robust so that even in the worst combination of all these errors together, it's still going to be stable, and it's still going to provide the response and the command tracking that you require. So. And then, I'm going to skip over the math, but basically the idea here is that we have this sensitivity and complementary sensitivity, which are two metrics, let's say, that tell us how much we react to disturbances or to noise. So basically, at low frequency, we are concerned about disturbances because we need to be able to compensate for, let's say, a change in the wind direction, for example. We need to be able, the aircraft needs to reject that. So it needs to basically keep going where it's being commanded to go, and not just let the wind blow it, somewhere else. So that's at low frequency. And at high frequency, we have this sensor noise, where basically we don't want to react to every little jitter from the sensors, but we basically want to also reject that and not act upon the noise. So you can see that this complementary sensitivity function basically is small at high frequencies, and sensitivity is small at low frequencies. So the point here is that we need to design our control law in such a way that we are reacting at the frequency at which the pilot wants to command the aircraft, and at which the aircraft needs to react to external disturbances, but we want to reject everything that's lower frequency than that and everything that is higher frequency than that. And so the frequency, let's say, that's critical for us is this crossover frequency. And you can think of it like the highest frequency at which the pilot can still command something, and the aircraft will still do it. If the pilot is trying to command something faster than that, like reversing like left right faster, the aircraft will just keep going straight. It will not react to higher frequency commands basically. And unfortunately, because these sensitivity and complementary sensitivity go against each other, we cannot have both, so we just have to make the best trade-off of both of these. And what we try to do with our control system is basically parameterize it in such a way that we don't have to design everything from scratch every time we get a new aircraft design, because even though like I'm working for 2 customers right now, but actually it doesn't mean that we're designing 2 aircraft. It actually, there's many iterations of every design. So like every, let's say, 6 months or every year you have a different aircraft design almost that we're basically working with. So we're, even for each customer, because they're also in their development process, we need to kind of keep up with that, and we need to basically be able to quickly adapt our control law for all that. So this is our basic what we call desired dynamics control loop. As I was saying, basically we are trying to parameterize it as much as possible. So this is essentially a PD controller, proportional and derivative. PI controller, proportional and integral controller, where we have this proportional path, which we call command, and we have this integral path, the proportional part basically ensures that we're tracking our commands, and the integral part basically rejects any disturbances that happen. So if there is a steady state error, basically that integral path will drive it to 0 and reject any long-term disturbance. Then we have this bandwidth gain, which is basically how we set our crossover frequency. So that's the only parameter that we really have to optimize. Everything else, all these fractions, these integral fraction, command fraction, and also this anti-windup, which is there for the purpose of preventing the integrator from winding up when the aircraft is not able to follow some command because it's on a limit. Like let's say you're asking it to accelerate, and already the engine is at the maximum power. If you keep winding up that integrator, then it will eventually, like if you then want to stop accelerating, you will, let's say, stop commanding the acceleration, but because the integrator has wound up, it will keep on accelerating. So even if you now want to decelerate, it will just keep on accelerating. So for that purpose, we have this anti-wind up where we basically take what's before whatever physical limitation we have, and what comes out of the limitation, and if there is a difference, it means that we're on a limit, then we're basically unloading that integrator. So this also has its gain associated with that, and we have basically these 3 gains, which have been designed carefully that are in a way that is reusable basically for any application. So the only thing we have to set is the bandwidth basically. So that simplifies a lot our design. The other important part, which I'm going to talk about, I guess, in the major part of the presentation, is that the aircraft response and the dynamic inversion together, they act as an integrator. So basically the whole purpose of the dynamic inversion is that we can design this same control law for any aircraft, because we're always going to take the real aircraft and the dynamic inversion, and together it's going to behave as an integrator. So we're only concerned about being able to control an integrator, which is very simple. Okay, so the important thing here is that the input to that dynamic inversion is the derivative of what we want to come out of the integrator, right? So this is basically what we call y dot desired, or also controlled variable derivative, and this aircraft response that we're controlling, that's called the controlled variable. The controlled variable could be, for example, velocity, or it could be position, or it could be angular, angle, or it could be angular rate, like how quickly the aircraft is rolling, how quickly it's pitching, how quickly it's yawing. So depending on what we want the pilot to be able to command, usually now for these electric vertical takeoff and landing aircraft, it's velocities or accelerations, because that's the simplest thing that the human can think of. And if you're, for example, I don't know, how many people here fly drones, or have a drone for, camera drone or something like that? Nobody? Okay, never mind. But basically, if you, a consumer drone, basically you're commanding usually velocities. So because it's really simple, you can learn it in 5 minutes, basically. So if you, let go of everything, it will just hover in place. So we're doing the same thing with these aircraft, basically. But on a fighter jet like the F-35, the pilot would be typically commanding angular rates, because we want the pilot to have a bit more control, so they, would be commanding, let's say, different parameters. Okay. So now, I've talked a little bit about these gains. So basically, we set this bandwidth gain such that we get the crossover frequency that we want. So if the crossover frequency is too high, it means that then we get issues with, for example, the fact that the aircraft is not a rigid body, but basically it's elastic. So, at high frequencies, what can happen is that parts of the structure are actually vibrating with respect to each other. So, you have, let's say, your engine mounted in a different place where the sensor that's measuring your angular positions, is mounted, and so you then get some difference between those two, and at high frequency you could, that could become unstable, and you could easily get into a resonancy, basically, and you could break up the aircraft. So that's actually one danger with fly-by-wire in general, that we have to check that we don't get this resonance before first flight. Basically, we do checks that are called structural mode interaction, where we basically power up the aircraft to where it's barely touching the ground, and we then inject some on purpose some sine waves, into the different effectors, and we let the aircraft vibrate, and we check that it's really stabilizing itself, that it's not growing, because if it grows, then in the air that would be a problem. And unfortunately, these what we call elastic modes, they are relatively low frequency for these highly, let's say, efficient aircraft. Like when they're electric, they are as light as possible, so the structure is as light as possible, so then it's more flexible even, and that's kind of where our difficulties come from. And then, if the bandwidth gain was too low, then we wouldn't be able to reject, every turbulence that we want, for example, etc. So that would also be bad. And also, if the pilot then commanded something, let's say they wanted to go right, they would command to the right, and there would be a delay. And now, the pilot would command more, and then, it would move right, and the pilot would command left, and they could get into this what's called pilot-induced oscillation, where, the human is trying to do something, and the machine is reacting with a delay. Then you can get this this issue, which is also very dangerous. So basically, that's the importance of setting the bandwidth gain. And then, the other gains, they have already been designed such that the system reacts as a first order or as a perfect, as a transfer function of 1, which is basically a perfect response. So that's those are these gains. So now the dynamic inversion piece is let's say the most complicated part. It relies on an onboard aircraft model. So we get from our customer the model of the aircraft, because when we're developing the control law, we also need the model for our plant, for basically what we're trying to control. So we need some simulation of the aircraft, because otherwise we wouldn't be able to test that what we're doing is actually working. So since they already give us the model, we use it for two purposes: for our simulation, but also we use it in our control law basically as a means to create this dynamic inversion in real time. So the onboard aircraft model, let's say it's running on the flight control computer, and what the flight control computer does is that basically every frame or every time step, it'll like simulate what happens if you move one effector, let's say one control surface 1 degree up, and it will measure or compute what the forces and moments on the aircraft will be. Then it will move, let's say it will increase an RPM on the one rotor by 10 RPM, and it will measure what would then happen. And it creates what we call the B matrix like that. So basically, if I'm not sure if you're familiar with state space representation, but we have this stability matrix, which is the A matrix, which gives us basically the stability properties of the system. And then we have the control matrix, which is the B matrix, which basically tells us what happens if you try to command some effector or something that basically if you send a command, what effect that command is going to have on the system. So the flight control computer computes that in real time, and once it knows what effects all these movable parts or these effectors will have, it will then compute what is the most efficient combination that will give us the forces and moments that we need. So we need 3 forces, 3 moments, basically, and we have, let's say, 20 effectors or 15 effectors, or a lot of moving parts. So there is an infinite number of combinations that we can get that basically that you can use to obtain the same forces and moments, but only some of them are better than others. And better means usually more energy efficient, so usually lower RPM or lower power is better, but also, let's say, for control surfaces, a deflection of a control surface that's not, let's say, putting too much stress on the airframe or on the control surface, etc., is better. So usually lower hinge moment is better. And there can be other specifications, like for these battery-powered aircraft, you can have certain rotors connected to certain batteries, and then you need to equalize the cells, etc. So there can be many criteria. We also try to equalize the RPMs a little bit for noise reasons, and etc. So there is many things that you can that are basically requirements for your design then. So now the important part is that when we receive this model from the customer, it's complete. It has everything. It has model of every actuator. It models, let's say, in the electric motors, like every almost like every winding, I would say. Like it's really detailed, and we can't fit that in the onboard computer. So we basically simplify it for that purpose. We take away all the high frequency parts, because anyway we're not going to be able to control the high frequency parts because our crossover frequency is lower. So we basically only need the propulsion forces, the aerodynamic forces. We need gravity, obviously, and basically that's pretty much it. And we also sometimes need like interactions between different effectors. So for example, when you have this multiple rotors blowing air, they interact between themselves. So if one rotor is blowing over another rotor, then it will change the forces and moment that rotor is producing, etc. So we need to model that, but we don't need to model things like the actuators. We don't need to model these elastic modes, like the flexibility of the structure of the aircraft, because that's really high frequency and that's really difficult to fit into an onboard computer. And we also don't do anything about landing gear forces. So like when you touch down, actually the reaction from the ground is really high frequency. Like there is the compression in the tire, there is compression in the oleo, etc. And all that happens so fast that the flight control computer wouldn't be able to react to that in any meaningful way. So we don't include that in our onboard aircraft model. And we then need to do something else. Like we need to have a different control law when we're on the ground, basically, and we switch to that different control law. So now to simplify it a little bit, because it's already complicated enough, let's say, we have, for example, customer that actually has 28 moving parts on their aircraft, and our computing power is just kind of getting to its top now. So basically, we can't ask for more. So we can slave effectors together. So we can, let's say if one surface deflects up, then usually we want the other on the other side to deflect down. So we can do that. But then we lose the redundancy. So if one of them fails, then the other one we will not be able to use it in an intelligent way to compensate for that. But we can do it in some cases, and we can also schedule some effectors. So like let's say we can, for example, change the blade pitch angle on the rotors as the speed changes, because that's always going to be done the same way. So it doesn't need to be controlled in an intelligent way. So we can do some things to simplify it and basically to take the load off the main control law, so that it doesn't have to, let's say, work as hard. Okay, so now just some more math about dynamic inversion. So this is what we call a state space representation. So X is basically the states of the aircraft. So typically we have 12 states. We have basically 3 positions, 3 velocities, 3 angles, and then 3 angular velocities. Sometimes the 3 angles can be represented in a different way. We use quaternions, so those would be 4 states. So then we would have 13 total states. And the x dot is the derivative of the states. So this is essentially our aircraft model. So we have some A matrix times our states plus the B matrix times our effector commands, and that gives us some state derivative. So if we want, for example, let's say to roll the aircraft to the right, we have some roll angle, and then we deflect some control surface, and that we have, let's say, some roll rate. It's already rolling. We deflect some control surface. That will produce a moment, and that's equivalent to an acceleration. Let's say a roll acceleration, and that's going to be this x dot. And then y is our, what we're trying to control, which is basically typically a function of these states. So the C matrix times the states, basically. And what we do with dynamic inversion is that we know what we want, and that's the y, basically, and we just need to get to what is u then, what are the commands to the aircraft, basically. So we invert these equations. So we basically write down the derivative of y, which is basically, cx dot. We expand that, we write it like that, and then we basically need to find what u is, right? So we rearrange it. We basically take the inverse of CB, and we put CAX to the other side, and we get that this is the commands that we need, and this has 2 parts. So this has this CB, C times B matrix, and C times A, and we call this one additive inverse and this one multiplicative inverse. And this additive inverse is typically represented by the aircraft model. So this is our onboard aircraft model. It's a little bit, let's say, tricky to maybe see like that. But yeah, this is our aircraft model, and this C times B is a matrix that we create we compute it every frame. So every time, every few milliseconds, I can say how much. So that way it's up to date. And let's say if there is a failure or if there is any limitation on any of the effectors, it's taken into account. So let's say you can have one rotor failed, for example, then we take that into account in this B matrix. We just say, okay, that rotor has no more effect, or it has just this effect. You cannot control it anymore. So then the control allocation will automatically use the remaining controls, and so you don't have to have like a special control law for every failure. It's the same control law. We just set a different limit on an effector, or different limits. What is the maximum and minimum RPM? Usually that would be the measured, whatever it has failed to do. So let's say it's still spinning, but it's just spinning because of the wind. So okay, so that's what we can give to that rotor, and everything we can do is just going to be distributed in the other effectors. And that has already been put to a lot of use in one of our projects. It's had multiple failures, I can say, and it has been able to mostly cope with that. Obviously, all only within what the aircraft is capable of. So if the aircraft cannot give you, let's say, enough vertical thrust, and you are hovering, you don't have any airspeed, you just are hovering, and suddenly you lose too many rotors, then the only way is you're gonna go down. But at least the control law can do the best in that situation, so it can still keep you straight, level, and just minimize the vertical speed, basically. So there's always these aircraft limitations that we cannot overcome. Okay, so I've already talked about this. Okay, yeah, and so this is just a detail that this CB inverse. It's not a square matrix, so we're not doing a direct inverse, but we're doing a pseudo inverse, basically, which means we have this weighting matrix, and that can basically tell us how much we want to use different effectors. So, like for example, if we have a well, let's think of now a little bit different example. We have this hovering aircraft that can that has 4 things it can do. It can tilt nose down, it can tilt nose down or up, left or right. So that's 2. It has a force up and it has a force forward. And let's say we want for the passengers to be comfortable. So let's say when we accelerate forward, we don't want the aircraft to go like nose down, because normally a drone, when you try to go forward, it will just pitch down and will just keep going forward. But we have these, let's say, means to create forward thrust. So we can say, okay, we want the pitch angle to be ideally like this, so that you can sit comfortably, and then you can modulate just the forces, the vertical, the forward force, and the bank angle to give you the response that you want. So we tell this weighting matrix that it's not supposed to use pitch. If it doesn't need that, it shouldn't. It just should keep the pitch stable, and it should just use the other effectors. So basically, it will be a high weighting in that case on pitch, and so basically it will, in the cost function, it will not prioritize that effector. But if there is no other way, let's say you want to slow down, and now you can only create a force forward, up, and pitch or bang, but you need to go aft. So then, okay, the only thing it can do is pitch up. So it will still do that. It's just that it will not prioritize it. Okay, and the final, let's say, summary. So by the way, this is the Armax helicopter. This was another project, past project. This is a Japanese helicopter, which it's used for agriculture, crop dusting, and so on. And it's completely autonomous. So dynamic inversion basically allows you to quickly reuse the same control law. So the desired dynamics is the same, and the only thing that changes is the aircraft model or the onboard aircraft model. It allows you to basically very quickly, create this for a new aircraft. But obviously the drawback is that it requires the aircraft model, so it has to be accurate. If it's not accurate, then you have an issue, because then if you have a mismatch between the reality and the model, then obviously it will work. It will accept some level of mismatch, but beyond certain level, it becomes unsafe. So we basically need to measure how much mismatch we can still live with. And then we ask our customers to basically provide the model within that accuracy. We don't model these high frequency phenomena, so we need to be able to react to them in other ways, which is basically by using feedback. Okay. We have these uncertainties. So for example, when we implement the aircraft model in the flight control computer, there is some lookup tables that basically don't have an infinite size, so they obviously there will be some approximation. We also don't model these actuator, sensor dynamics, elastic modes, the flexibility of the aircraft structure. We also don't know exactly the weight and the center of gravity of the aircraft, because obviously depending on how many passengers and how much luggage, etc., you can't really weight everyone before getting on board. So we have to accept some mismatch there. We design it for some middle ground, but also let's say one of our projects is a cargo aircraft, which there has to be some input from the operator that will, tell it like approximately what the weight and what the center of gravity is. And yeah, well, also we don't know the air density perfectly, because we can only measure temperature, pressure, humidity, but we cannot, know exactly. And we also don't know wind until it's already there. So basically, and we actually have an estimator of wind, which uses the onboard aircraft model, which is quite a sophisticated thing also, but it's still only got some accuracy that's not always perfect. So we need to be able to cope with those uncertainties. So yeah. Yeah, I think this is the last slide actually. So yeah, it's just basically showing where these uncertainties are, and yeah, I think that's pretty much that's the end. That's the last slide. Yep.
I can imagine how far there's not so much time.
No worries. I tried.
I can imagine this was so great challenge. Thank you very much for the presentation. Do we have some question, please?
Sure.
So my question is, why a first order system? We can easily model it as, let's say, if we want to model linearly, we can have second order system, and then we will get to have more options for the poles or the zeros.
Right.
Can you repeat, please?
Yes. So the question is why we use the first order system and not multiple order system. Right. So actually, yeah, what I was presenting here is a little bit of a simplification. So the desired dynamics part, which I was showing you, we use it 4 times. We use it it's like nested inside of each other. So we have an inner loop which controls angular rates. We have a loop around it which controls angles. We have another loop around it which controls velocities. And we have another loop around it which controls position. So basically, it then becomes a 4th order system. But you could do all that with one set of loops. Like you could just have that at one level. That's a choice. So you could do it like that, but you can also do it like we do it, which is basically just do the first order approach, but then nest it inside of each other. So yeah.